Hey everyone, welcome back to the dining room shop. So after a long wait, I finally got part 4 of the Precision Spindle Metrology series for you. Today we're going to wrap up a couple loose ends on the measuring the different sensitive directions, go over error separation techniques, and then excitingly do a demo at the end where I actually measure something rather than just yap like I've been doing. But let's go ahead and jump into it. So last time I used the example of making a fixed sensitive direction radial error motion measurement to have all of our discussion. Right, so indicator fixed on the side, measuring the radial error motion at one location. What about other sensitive directions? Well, for radial rotating sensitive direction, you might imagine an equivalent metrology arrangement where now the indicator is mounted on the spindle, since the indicator represents our sensitive direction, and we want to measure the rotating sensitive direction. You could have a ball fixed sort of in the middle, while the indicator is fixed to the spindle rotor itself, something like this. So it'd be kind of impractical in reality, since we'd need some sort of slip ring or something to get the signal back from the electronic indicator without wrapping our cord like a spaghetti noodle around the spindle. Pretty whack. Luckily, we don't have to do this. As you may recall in the sensitive direction video, I mentioned you can just take two orthogonal fixed sensitive direction measurements, two 90 degree from each other, one here and then one here, and just calculate the fixed sensitive direction error motion mathematically. So if our first measurement from the side, we'll just call that the X measurement. And then we have another measurement from the top, which we'll call our Y measurement. And these are both, of course, functions of theta, since we're measuring around the full 360 degrees. The rotating sensitive direction error motion, which we'll just say S sub RSD, is the X error motion times the cosine of theta plus the Y error motion times the sine of theta. So we can just take two fixed sensitive directions and combine them like this to get the rotating sensitive direction. I could have just told you that to begin with, but the reason I brought up the thought experiment of trying to directly measure rotating sensitive direction error motion is because, funnily enough, that's the exact same setup that the Moore universal measuring machine used to measure roundness. You can see in this in the photos from Foundations of Mechanical Accuracy here, they actually did have an electronic indicator mounted in the spindle and used a slip ring to get the signal from the LVDT back out. Kind of a crazy setup. In that situation there, they were not measuring spindle error motion, they were checking roundness, so the spindle's error was assumed to be very small with respect to the roundness error of the part. But it's kind of cool that they were still able to do that. So there's your radial error motion covered, rotating and non-rotating sensitive directions. Now I also must mention measuring axial error motion. There's one element here where you have to be careful regarding the centering of your indicator in the artifact. And the reason is the 1 UPR error, the 1 undulation per revolution error. When we're doing radial stuff, a 1 UPR error is run out. It's not real because we can just move the artifact to center it better and eliminate the runout. With axial error motion, you absolutely can have a 1 UPR error, and it is a real spindle error. Going back to this model from the first video, you can imagine if this, right, so in this particular instance, the axial direction is constrained by this back face of the shaft here. And if our support is off-centered and this thrust face is not square, you can absolutely imagine how, as it rotates once per revolution cyclically, the shaft will be pistoning in and out like this. So that's a 1 UPR axial error, which is real. It cannot be discarded. The problem is, depending on your setup, if you're not careful, you can introduce a 1 UPR error that is not real, and it's a result of a poor setup. This occurs when your indicator is not perfectly centered over the spindle axis. So there's two types of artifacts we can use here. We can keep using a ball like we've been doing, or we can just use something like a flat, an optical flat or something. It doesn't even need to be as nice as an optical flat, because when you think about it, if you're indicating right over the spindle axis, you're not actually picking up any of the artifact shape at all. Your indicator is at a single point on the artifact, and you should have zero surface velocity. So this also means that there's no need to do error separation either, since the artifact form error is irrelevant in the perfect setup. Your indicator is directly over the axis of rotation. The trouble begins when your indicator isn't exactly over that axis of rotation. Now, if your flat artifact isn't perfectly parallel, or if your ball is running out a little, you'll see a 1 UPR error that is very difficult to distinguish and separate from the real error. If the ball diameter is large and the runout is small, it's not horrifically sensitive to this, but it's still something to be careful of. To be clear, in order to incur this error with the ball, both the ball and the indicator must be misaligned from the spindle axis. So if the ball is running out a bunch, but your indicator is still exactly centered, you still wouldn't see a height deviation necessarily. But if your ball is running out and your indicator is off center, then you can see how you'll have a cyclical up and down once per revolution, which is not real error motion. In order to incur this error with if you're using a flat as an artifact, the flat basically would just need to be not parallel or not flat with respect to the axis of rotation, not perfectly normal to it, and your indicator would need to be off-centered. Most insidiously, it's theoretically possible for this 1 UPR error from misalignment to be out of phase with a real 1 UPR error from the spindle, and have them cancel out to some degree, leaving you with a result that's better than reality. But yeah, just remember it's important when measuring axial error motion to take care to center your artifact and indicator very well, because you can't just discard the 1 UPR component in the analysis like we do with radial error motion. Finally, we have tilt error motion, and you can basically imagine how you might measure this. If we take two different radial error motion measurements spaced apart by some length, we can subtract the one taken closest to the spindle from the farthest away one, divide it by the known separation length, and then take the inverse tangent of the data set. This will yield the tilt error motion in angular units instead of linear units. So say we measure the error motion here, put it on a 6-inch riser or something, and then measure it again up here, and we can get an angular error motion. The tilt error motion becomes particularly pernicious when you're working far away from the spindle nose, so it's worth taking into account if you're making or measuring a very long or tall part, or a part of a very large diameter. So if we want to know the total radial error motion, effective radial error motion at a given distance from the spindle nose, we multiply the tilt by the distance from the spindle nose, and then add the basic radial error motion back to that to get the total effective radial at that point. The same goes for axial error motion at some large radius away from the center line if you're measuring out here or something. Technically, when we measure radial error motion at the spindle nose, to be precise, we should admit that even right at the spindle nose, it's still a sum of pure radial plus a little bit of tilt, since in theory it's rotating about the center of the bearings, which is inside of the spindle where we can't get to. But since we're so close to the center of rotation, we usually just call that our zero for radial error motion and go based off that for everything else. With that out of the way, we can now get into what to do when your artifact isn't perfect and when we can assume that it is. So up until now, all of the discussion of procedures has just assumed a perfect artifact, a ball that is absolutely spherical, perfectly round, and contributes no error whatsoever. In reality, of course, no ball is this. So as a basic rule of thumb, we can use kind of an order of magnitude rule to see what we can assume. If the ratio of the artifact's roundness to the spindle's error motion is less than 1 to 10, then we can usually assume that the artifact is perfect and just directly measure the spindle error motion as I've described. If the opposite is true, and the spindle is 10 times better than the artifact, first of all, maybe artifact is the wrong word to use, but in that case we basically have a roundness tester, where the spindle is nearly perfect and those errors can be assumed to be 0, and whatever we measure is mostly representative of the roundness of whatever's on the spindle and not the air motion itself. When the artifact does not satisfy the requirement of being 10 times better than the spindle, it begins to get difficult to make definitive statements about the spindle's air motion, as what air motion we measure becomes mixed with the non-negligible roundness error of the artifact. And practically this almost always ends up being the case when measuring an ultra-precision spindle. If we want to directly measure the air motion of an air-bearing spindle with an air motion on the order of 1 microinch, say, we would want an artifact with a roundness of 0.1 microinch, or 2.5 nanometers about. Now the crazy thing is, Professional Instruments actually does have a ball which is round to about 3 nanometers on the equator, which is absolutely insane. So they technically could do that. But for most people in setups, your artifact will almost never be that much better than your air-bearing spindle. In the video where I was showing off the roundness tester, I found out that this artifact here was nowhere near as good as I thought. This is round to about 10 microinches or so. So how can we use this to measure a spindle which is likely going to be 10 times less air motion than this is round? To remove the uncertainty of the mixing of the roundness error with the air motion, we like some method of air separation, so we can isolate the roundness error from the air motion of the spindle. Luckily, this is a field of study which has been very thoroughly explored, so we can take a look at a couple different methods of accomplishing this. So there's a range of different ways of doing error separation that vary in degrees of mathematical complexity. What I'm going to go over in detail today and actually use is Donaldson reversal. It's a straightforward, dead simple method that anyone can understand and do themselves. Beyond that, I'll briefly explain a couple other methods and their pros and cons, but I'm not going to go too deep on the math in this video, partly because it would be a little alienating to a lot of viewers, but more honestly, I don't feel confident enough in my own understanding of it to explain it to others. It's far more complex to implement than a simple Donaldson reversal. But I'll still put this stuff up on screen for those with stronger mathematical proclivities to pause and ponder about. Anyways, let's take a look at the most basic way of doing an error separation, the Donaldson reversal. Again, in the context of fixed sensitive direction radial air motion measurement. So we have our artifact, our measuring device, and our spindle here. First, I'll mark each one with an index marker to sort of keep track of where we're at. So we'll say this is 0 degrees on the spindle, stator, 0 degrees for our rotor, and then 0 degrees for our artifact there. So step 1, we take a radial air motion measurement, just like before, and take that data set there. We subtract our 1 UPR error in the computer, and we'll call that first data set our M1, our forward measurement. Then we do two things. One, we move the indicator 180 degrees to the other side of the spindle stator specifically. And with it, we will also index the artifact 180 degrees, like so. From here, we take another measurement, just as we did before, subtract the 1 UPR, and we'll call this M2, or our reverse measurement. So what have we done by doing this? Well, our first measurement, M1, consists of two things. The spindle error, which is what we want to know, but it also contains the roundness error, which we'll just call R. And this is the problem, right? It has both added together and we want them apart. But think about what happened when we flipped the indicator and the artifact around. The artifact maintains its relative orientation to the indicator. That index mark was always pointed at the indicator body there. However, because now we're on the back side of the spindle, the error motion sign is basically flipped. So basically, if before the spindle had an error motion at one point during its revolution where it moved to the right a little bit, say 10 microinches, in the first measurement that would have been read as positive 10 microinch displacement. Now that we're on the left side, that would be sensed as a minus 10 microinch displacement, as the ball would be moving away from the spindle. So the second measurement consists of the roundness error as before, that hasn't changed, but the spindle sign has flipped, so it's minus s of theta. And this is perfect. Now we can add these two equations together, and the spindle error terms will cancel since the sign's flipped. So we can get m1, and we'll just simplify and leave out the thetas for brevity. m1 plus m2 equals 2r, which, you know, is basically just to say the roundness error of the artifact is the average of the two measurements. Simple as that. And then, of course, we want to know the spindle error motion. We take the difference of these two equations. So spindle error motion, s of theta, is m1 minus m2 over 2. There we go. There is our spindle error motion separated from and uninfluenced by the artifact roundness with just two measurements. So that's Donaldson reversal for you. It may look familiar, as this generalized reversal method can be used in many contexts, you know, like inspecting a straight edge with an imperfect reference or something like this. There's also a derivative of this method for measuring on the face of the spindle for tilt and axial measurements. It's called a Essler reversal. But yeah, that's Donaldson reversal there. From there, we can look at a couple other different methods of doing error separation. The motivation for developing them stems primarily from the main downside of Donaldson reversal, which is the need to unmount, index, and then sort of redial in the artifact, as well as unmount and index the indicator. Unless accurate tooling is created to streamline this process, it can be a little time consuming and sort of just manual and slow. We'll see in a second when we actually perform this reversal in real life that this is generally true. It would be convenient if we could do error separation in one shot, or at least in a way where we don't have to mess with the artifact and keep unbolting stuff and rebolting it. One way to do this is the multi-probe method, credited to David Whitehouse. So here, I don't really have a good physical representation of this setup, but if we have our spindle here with our artifact on top of it, we use 3 probes. We'll just say they're cat probes, and they're going to be looking at the artifact from 3 different angles around the spindle. Now these are not evenly spaced around the spindle. The reason they're not has to do with the math underlying the approach. Without getting too much into it, the issue is harmonic suppression. So basically, if we had them spaced evenly at 120 degrees, we wouldn't be able to see any 3-lobe errors, for example. It's roughly analogous to how if you're using a V-block to inspect roundness, the angle of that V affects the ability to see different frequency roundness errors when checking roundness. So we pick a set of angles which seem random, but they allow us to see and separate errors up to 225 UPR for the particular set of angles that Eric Marsh came up with, for example. There's this really beautiful plot from Stephen Kappa's PhD thesis that shows the severity of harmonic suppression for any combination of probe angles. It's really nice looking. But yeah, for those who are more mathematically inclined, I'll put the math up on screen so you can see it. Basically, we take 1 revolution's worth of data. We have 3 different data sets at these 3 different angles about the stator, and we can treat things as a Fourier series and sort of separate stuff back out. But you can look at it here, and if you'd like to figure it out, then be my guest. So this method works well, but one of the potential drawbacks is the requirement for very good matching between the three probes. If one probe measures 10 nanometers where another would call that same displacement 10.1, this can cause a lot of trouble in trying to achieve accurate error separation. So a variation of this approach is to use only one probe, but index it 3 times, and to generate the 3 data sets necessary for error separation. And this, so you take one measurement here, move the probe to a new place, another measurement there, and then a third place, a third measurement. And this seems like it maybe not as good, but it turns out this is the method used by professional instruments for the most accurate of error separations when they measure their spindles. And what enables this is very high quality tooling, which allows them to very quickly and very accurately index the cap gauge between 3 different locations. And the artifact remains undisturbed throughout that whole process, so it doesn't need to be redialed in or moved at all. Okay, so let's actually measure a spindle. I'd like to introduce you to one of the most cursed metrology setups of all time. It's a little rig I built to do a Donaldson reversal here. So the spindle we're going to be measuring today is a aluminum Model 3R blockhead, which you've seen before on the channel. And we're going to be measuring the fixed sensitive direction radial error motion. Here's the setup. The spindle is resting on this stand here. This is a kinematic coupling, which looks like it's about to fall off the surface plate, but it's just because it's bolted down through this through hole in the surface plate here. This has nothing to do with the metrology at all. It's just a stand that I've devised so this can sit in a stable manner and it's not distorting the housing at all. On the bottom of the spindle, I've added, just with some 3D printed stuff, a little non-contact optical encoder to keep track of the spindle position, so we can record our data. There, the spindle just sort of locks in like that. The encoder doesn't need to be anything fancy. It's just got 4,000 counts per revolution to provide our angular feedback. We don't need arc-second accuracy or anything. We just want to know generally where we took a data point. Now on the top we need 2 things. We need a way to index the artifact 180 degrees, of course, and a way to index the indicator 180 degrees. Some of you may have seen my recent video on the flexural kinematic coupling, where I proposed the ball be initially dialed in at some location on the coupling here. It was sitting in this little nest before, and then we could just pick up the kinematic coupling and move it 180 degrees, put it back down, and that would be good. Unfortunately, this idea didn't work out due to me discovering the bolt hole pattern actually was not nearly as concentric with the axis of rotation as I thought. So indexing, you could get it dialed in at one location, lock it down, but then if you rotated it 180 degrees, you would have an unacceptable amount of runout. Of course, the software removes runout, but if the runout is greater than the full scale of the indicator, this no longer works. So the new solution is low-tech, and we've gone back to a simple just ball sitting on a plate, which gets manually indexed to an alignment mark on the indicator holder each time, and it doesn't get bolted down or anything. It just gets manually indexed and then redialed in at that new index location. So, I mean, you may also ask, why not just keep the coupling that I already made, and then each time, you could still use that for indexing, but then just redial in the ball every time you index it. Well, the reason is when trying to dial stuff in on the micron or sub-micron level, the contact interface between the two objects that are moving relative to each other is very, very important. So a non-flat plastic surface sliding on a non-flat plastic surface is a stiction nightmare, and it's very difficult to dial in to the necessary levels. Stiction combined with a squishy plastic object makes very small incremotion very difficult. And the non-flatness means that when you finally do get motion, it might just pivot about some high spot on the edge rather than smoothly translate in the direction that you desire. So the ideal interface for dialing stuff in would be two very, very flat ground surfaces. And some static friction is good. We want to make sure that the object only moves when sharply tapped with a hard object, and something like the indicator force doesn't cause it to move. So we want some static friction. Stiction plus the elasticity of the objects is the real problem. That causes a large storage in energy, so when it finally does overcome the static friction, the move is much larger than you'd like it to be. We also want the so-called center of friction to be in the center, so that when hitting through the center, no rotations or pivoting occurs. This is another place where stoning can provide great benefit, knocking off the high points and providing an evenly distributed friction. If there was a ding or something on the edge here, and I tapped it in this direction because I wanted to move it in this direction, if there's a large patch of friction here, it would tend to rotate, and so you'd get direction not just in that direction but also a little over there as well. So having the surfaces be very flat is of course good, but something like a lapped surface can actually start to cause more problems than it solves because they're so flat. They have a tendency to try and ring together during this process and start to cause non-centered friction and these strange pivoting motions. That's actually one of Dave's 50 tidbits. I forget which number it is, but the ground surfaces go together better than lapped surfaces. That's the reason why. This particular plate, unfortunately, it wasn't able to grind. It's the faceplate from a little miniature lathe, but it's turned relatively nicely with a PCD insert. So it's nice and flat, and it's been stoned off. And this gives the sort of nice smooth interface that makes the dialing in good. And I'm pretty easily able to dial this into a half micron or better, no problem. That being said, it technically doesn't need to be dialed in that good, as any reasonable amount of runout can be removed by the software, but I enjoy dialing stuff in. Some people don't, but I find it quite fun. If we put that tangent aside, we can move on to the real abomination of this setup, the plastic, what I'll call the gauge nest. I don't know if that's the right word, but that's what I'll call it for now. The idea here is identical to that of the original ball holder. So the nest mounts kinematically to the spindle via these three balls here, and those are on a little flexural kinematic mount. So 3 balls can sit in the 3 holes, and because there's six holes within or around the perimeter of the stator housing, we can pick this up, move it to the other set of holes, and get a 180-degree indexing. So unlike the other coupling, which was just gravity preloaded, this one is held down by 3 screws, and those 3 screws bear on these little spring leaf things that are very, very compliant. So these don't generate a ton of force, and importantly, it doesn't over-constrain it. This keeps it relatively non-influencing in that regard. And tweaking the preload at these 3 points, I can very minorly deflect the coupling and tip and tilt, which allows for some basic zeroing adjustment, but most of the zeroing can be accomplished just using the electronic zero on the indicator there. I was afraid that having a separate adjustment mechanism built into this would be too much of a sacrifice on stiffness. Stiffness is of course something I really tried to optimize for here, since it was made out of plastic in fact. And this strange pyramidal design helps accomplish this. Pure tension and compression is of course desirable for maximum stiffness. The gauge itself, if you haven't noticed, is the hallowed Brown and Sharp 599-981 indicator, which was recently sent to me by one R. Renzetti on the internet. Very, very grateful and deeply honored to now have the privilege of using this thing. Really cannot express my gratitude enough. For the unaware, the 599-981 has a flexure-based pivot that the arm pivots about. And this is super important for realizing these sub-micro-inch displacements. There's no backlash or sort of slop in the joint at all. There can't be. And especially in this situation where we're sort of loading the indicator in this direction a little bit just due to the friction, it's really important to have a nice, tight, slop-free joint like this to get the resolution that we want. It's theoretically infinite resolution, right? So that's sort of the beauty of it. The indicator itself just mounts via this dovetail clamp here, which you can sort of see. It's a little bit different than sort of the standard ones on indicators. You can see it doesn't clamp on the inner, just on the inner walls of the dovetail. It contacts on these 2 points spaced as far apart as possible from each other. Again, just to try and maximize stiffness of the joint there. So you're probably wondering, why build this strange plastic contraption rather than use my great brand new, ultra beefy indicator stand? Well, believe it or not, this setup here is actually stiffer than if I just indicate it with this stand over here. While it is made out of PLA, the metrology loop here is tiny. If you imagine the structural loop, it's just this little, going through the frame, straight through the bearings, and then back up again. As compared to this guy over here, where the loop goes all the way down through the table, through the stand, and there's lots of length and sort of span for bending moments to act over. As such, the natural frequency also ends up being higher, so the result is a setup that's more immune to vibrations as well. And in fact, the steady-state vibration noise floor of this setup is as good, if not better, than when I had the whole plate balancing on those mountain bike inner tubes in the dead of night, like I had in that other video. And right now, this is sitting on nothing other than its standard sort of firm rubber feet. So, it seems like it might be floppy, but this ends up actually being better. Not to mention that if I did use the indicator stand, indexing that would be a problem. I would need to find a way to accurately index my whole spindle in a nice stiff way. And of course I couldn't be using this stand either. This is far too floppy to take a measurement through this structural loop with. But anyways, while this is stiffer and it's good for that reason, thermal expansion is of course the big con that you can point at for a 3D printed solution like this. And this is managed by two means basically. For slow global temperature changes, for this sensitive direction, of course, being this direction, if we look down at the top, the indicator is mounted as close as possible to the center of this whole structure, right? So if the plastic grows and shrinks in this sort of XY plane here, this is as close as possible to the center. So due to symmetry, we should see minimal change in this direction, just apart from the change in size of the indicator body itself as that changes temperature. So that helps a lot in that direction. In the vertical direction, of course, up and down like this, there will be a lot of shift with temperature. But because the indicator is measuring on the side of the ball, on the equator of the ball, Motion in this direction, it's sort of a second order effect. You know, it's a small angle thing. So for very small thermal expansions, that's more or less negligible. Now, of course, non-uniform changes in temperature are the real killer, right? If one of these arms starts heating up more than the other, you know, due to convection from the air conditioning or just radiation from my body being kind of near it in general. And so this is addressed by this revolutionary idea of a shield. Funnily enough, this is actually from a scanning tunneling microscope that someone sent to the channel. So it's still doing its original job. The difference is it's now blocking electromagnetic radiation many orders of magnitude higher frequency than before. And it also doesn't need to be a Faraday cage. But just by setting this on and letting it sit for a minute or two before we take the measurement, that lets sort of all the air currents settle down and blocks radiation from my body that would be trying to heat it up. And so the drift is minimized to an acceptable level. Okay, so with that design review out of the way, let's actually go ahead and take a measurement. So I've got underneath here the ball's dialed in, it's locked down, it's been sitting for a minute or two. You can go ahead and zero it out as best we can. Now, a brief note on how the spindle's being driven for this. I want to go at a consistent speed to get a consistent reading, and this is the setup for driving. I've got a brushed DC motor, tiny little guy, with a piece of silicone insulation, wire insulation on the outside of it. And that is what, just touching on the rotor there, drives the spindle. Super low torque necessary, but super non-influencing as a result. No need to get too fancy there. So what we'll do is we'll go ahead and start a measurement. I'll, over here in MATLAB, hit record, and then I'm going to turn the power supply on, and that's going to start the spindle spinning. You can sort of see it rotating underneath there. Wait for the index pulse, and now we're recording. There you can see the data streaming in MATLAB. And you can see also on the top scale here, just for fun, I've dialed it in very well for no reason, but that'll record 4 revolutions worth of data here at this relatively consistent speed. Almost done, and I'll stop it there. Okay, so here's the result from that measurement. So this says roundness because I'm using the roundness testing program to do this. And this is, if you've watched the videos I've done on the roundness testing, you'll recognize this sort of data output here. So the raw data looks quite nice. And in fact, this is really spectacular. Remember, this is 4 revolutions worth of data overlaid on top of each other. The y-axis is in microinches, and look how repeatable this is over the 4 revolutions. I mean, that's really, as I was saying, that's quite a bit better vibration and stability performance than the other setups I've used in the past. So let's see, 1.96 versus 2.4. So just about, at the worst case, maybe a half micro-inch repeatability. But the whole point is this averages out 4 revolutions worth to get our output. So again, so this says roundness, but technically it's a combination of roundness plus the spindle error. The peak to valley there is just about 12 microinches, so it's mostly the ball roundness. And just coincidentally, look at that, I dialed it in to 1.76 microinches. So that's fun. Of course, it's impossible to actually tell that it's that good based off the scale on the indicator. I basically just got lucky there. But so there's our first revolution. Okay, so now you can see, and I haven't put the cover on just yet, so you can see this is in fact real. I flipped it around the 180 degrees on the stator. The artifact is also flipped around now. Redialed it in. Maybe not quite as good, but at least decently again. So I'll go ahead and just plop this on top, and this will change the reading for sure, just because of its weight and deflection and stuff. Get it on there in a way that's reasonably stable. Okay. Now I'll let that sit for a minute longer, re-zero it, and take our measurement here. Okay, so we've hit record, waiting for the index pulse, and there we go. Now we're recording that reverse measurement at 180 degrees. And there we go. So here's our reverse measurement. Let's see. Right off the bat, it's, visually you're not going to be able to tell a difference, if we're being honest. Remember, the roundness error will look the same for both measurements. The thing that's reversed is the spindle error, which is much less. Ooh, now looking at this is a little annoying. There's thermal drift there, right? That's what we're seeing. The full revolutions all look identical, which is great, but unfortunately there's a bit of drift between them all. Now that can be okay, so long as this matches up reasonably well. What I've seen is when there's extreme thermal drift before, what I've seen is you can still see sort of a step in the average of the four data. So I'll go ahead and actually retake this, let it sit a little longer, and retake the measurement just to see if we can improve that a little bit. Okay, so I redid that measurement and got a much more repeatable result. But now we can go ahead and do our reversal. I have that in a separate program, and basically here you can see the gist of it all. The artifact roundness is equal to the average of the two data sets, and the spindle is the difference divided by 2. So we can go ahead and run this, and here we have it. So what are we looking at here? The output, we can just look at from the bottom. It finds the roundness to be just under 11 microinches, and the total synchronous radial error motion to be 1.1 microinches. So quite good. The S to A ratio is just the magnitude difference between the spindle error motion and the artifact roundness, and I'll talk about the applied index error correction in a moment. But in this plot we can see the roundness of the artifact in the blue line, and then the red line is the spindle error motion plot. So you can see much better than the spindle, or than the artifact. And then here is the spindle error motion plotted by itself. So look at those scale lines, and those are in microinches. So minus 12.5 nanometers, plus 12.5 nanometers. So pretty incredible that we're able to measure a spindle error motion to this level in the dining room shop. But I wanted to briefly mention, what is this index correction thing? So one of the tricky parts about this is, since I'm doing the indexing by hand, there could be some error in my indexing, and the degree to which my reversal will perfectly sort of cancel out the artifact or the spindle error is related to how well I can index it. But that also depends on the spatial frequency that I want to cancel out as well. Higher spatial frequencies require a finer accuracy of indexing in order to be exactly canceled out. So what my code does is we have these two data sets, and if we just do the Donaldson reversal with them as is, we'll get some result. But what the code also does is basically just tweaks the angle, the relative angle between them a little bit, plus or minus a few degrees, and looks for the angle at which the RMS spindle error motion is minimized. And this is a good way to basically correct for any minor angular indexing errors. So this plot shows basically what the results of that is, or showing that it's working. 0 is the exact 180 degree index, sort of as from the raw data, and then this goes plus or minus 45 degrees here, and shows the peak to valley error motion and the RMS error motion as it sort of tweaks the relative angle between the two data sets. So for this particular Donaldson reversal I just did, it needed to tweak it by 0.63 degrees to find the basically best match. And you can see, this is just as an example here, as the angle, the mismatch in angle goes away from 180 degrees, this is the spindle error motion plot, but it gets worse, right? This is not actually the spindle error motion. It's getting sort of bleed through from the roundness error. And as we get closer and closer to the exact 180 degree flip, that gets minimized. But that's what that does. But here's the final results, and I'm quite pleased with that. But yeah, that's measuring fixed sensitive direction radial synchronous error motion. That is worth noting that none of this was taken into account asynchronous error motion, because for this spindle it's basically 0, or at least my metrology can't detect that. Now the roundness testing software does have that little plot that shows the asynchronous, and that's always well under a micro-inch, smaller than I can detect. But yeah, hope you guys found that interesting. I'll probably do another part for this series at some point. There's a couple other topics like dynamic runout and things like this, which I think might be worth mentioning, but for now we'll call it good. Let me know if you have any questions in the comments. And in the words of the great Ben Krasnow, okay, see you next time. Bye.